Alright, so I'm going to be recording a short lesson over quantum numbers and electron configuration. And before we get into electron configuration, I think it's important that we understand quantum numbers first. Because in order to understand electron configuration, you must have some sort of general understanding of what quantum numbers are and what they represent. Alright, so let's go and start off with the principal quantum number. It's so the whole point of quantum numbers is basically a way to generalize where inside of an atom can you find a certain electron, right? So we all know that electrons do not stay put in this exact position that um, you might say they are. They're actually always moving around throughout the electron cloud, right? But quantum numbers, you could it's basically saying, okay, if you were to freeze time at a certain moment, uh, quantum numbers basically tell you where that electron would be found. All right. So I like to always think about the principal quantum number as kind of like what city you live in. All right. So let's say you're shipping a box to a friend, and you're asking them, okay, where do you live, so I can ship this box to you? And they decide to get kind of strange, and they tell you, okay, they make it a game and they make you guess. So they say, okay, I live in El Paso, right? That's very, very general, right? It doesn't really tell you where they live. It doesn't tell you where to send that box. Um, but it gives you a general understanding of where they might be, all right? A very, very general understanding, okay? So if you were to try to find that friend of yours to send him the box, it might take a very long time because you have to search every single house in El Paso, all right? And that's a lot of houses. So the principal quantum number can be measured in anywhere between 1 through 6, and I think that's all you have to worry about for Chem 1. Um, so I don't think you should be seeing anything with a principal quantum number of 7, and I'm not even sure if that exists. But anyways, let's go in and get to it. So the principal quantum number, I'm pretty sure you guys have seen something like this. It's called a Bohr model. So let's say we're talking about an atom of nitrogen, all right? Nitrogen in its neutral state has 7 electrons. So remember how you guys saw it in middle school maybe, or even in high school, where you write 2 electrons in the first little circle here, and then in the next one you put 8. And in nitrogen's case, since we already put 2 in the third one right here, we just put 4, 5, 6, 7, right? So basically what the principal quantum number is we're labeling this energy level as the first energy level and this energy level as the second. All right? So it's very, very general where that electron is located. It's not very specific at all. But yeah, that's the principal quantum number. Just a very general area of where that electron can be found. All right? So let's talk about the angular momentum now. Okay, so angular momentum is kind of like saying, okay, I live on this apartment block, all right? So like let's saying I don't know what the apartments are. Let me just call them the chemistry apartments, right? So that's not very specific either. It might take you a little bit of time to find your friend, right? Because some apartments can be very big, so it's kind of inconvenient to knock on every single door. So yeah, your friend's basically telling you, I live at the chemistry apartments, which is getting a little bit more specific, but not quite as specific as we want to get. All right. So angular momentum. This chemistry apartments thing is a very, very simple way of viewing it. So, but in reality, what we're trying to talk about is the s orbitals, p orbitals, d orbitals, and f orbitals. All right. So this is what an s orbital looks like. This is what a p orbital looks like. It actually has a, this is a py. You also have, sorry, that's very bad, a px. And imagine this as in the z-axis, so pz. And I'm not actually that good at drawing the f orbitals, but just know that an s orbital, a p orbital, and a d orbital, and a f orbital they all look different. and you can Google d orbitals and f orbitals because I'm not too confident in my ability to draw them. So I'd rather not, just so I don't confuse you guys. Um, so yeah, you can look at this little chart right here. It's actually located in your guys' workbook. So you have S, and this is what L is equal to, all right? So L is equal to 0, and then for a p orbital, it's equal to 1. For a d orbital, it's equal to 2, and for an f orbital, it's equal to 3, all right? So it's kind of like saying, okay, I'm located at the 0 apartment or the 2 apartment. You know, it doesn't really make much sense when you talk about navigation, but it's basically what this angular momentum is measuring, right? So now let's talk about the magnetic quantum number. Now the magnetic quantum number is basically telling you, okay, which room in this apartment complex are you located in? All right, so we're gonna imagine that our apartment complex is 2 stories. So let's go ahead and just draw it like this. I'm not a very good artist, so let's say that this is the ground floor. All right, that's the floor separating the first and second floor, and we'll call this a room. We'll call that room this room and that room. All right, so this is a room, that's a room, that's a room, that's a room, that's a room, and that's a room. All right, and I'm drawing this halfway between the magnetic quantum and the magnetic spin because they both have something to do with this diagram here. All right, so magnetic quantum number is basically the room. All right, so um, you can measure it as the following. All right, so for example, for an s orbital, you're going to follow this general formula. All right, so m of L is always going to be equal to negative L, and it's going to be in the range of negative L to positive L. And I hope you guys know that this bracket thing right here in mathematics is it demonstrates a range, and so that's what we're going to be using. All right, so S, as you can see up here, S is equal to 0. All right, when you're considering angular momentum. So the range that of an s orbital for a magnetic quantum number, so m of L is going to be equal to negative 0 to 0, which is also just equal to 0, right? So when you see magnetic quantum number and you're talking about an s orbital, just know it's always going to be equal to 0, all right? But now let's say you're talking about a p orbital, which is equal to 1 over here on the angular momentum. So the range of p orbitals is equal to negative 1 to 1, all right? So you draw that out completely, and it's negative 1, 0, and 1, right? And what I drew right here, this apartment complex, I'm actually trying to denote a p subshell, all right? So we're going to call this the negative 1 room, the 0 room, and the positive 1 room, all right? And remember that although they have the same room number, there is different floors. So maybe this is like room 11, room 10, room 11 as well, and this one up here is room 21. You know, that's not very important, but just make sure you understand that point right there. Okay, so so if we were to ask you for an electron found right here, we would say, okay, it's in the negative 1. All right, that's the magnetic quantum number, and it's very, very it's not proper to say, okay, this electron is going to be exactly right here, because electrons are always moving around, and the professors are not going to ask you for a question like that on the exam. All right. Something you might see is, okay, which of the following m of L values are appropriate for this orbital or this subshell? And if they give you, let's say they gave you an s orbital, so they just gave you something like this, and okay, so this is room 0. Let's say they gave you m of L values of negative 1. Would you say that negative 1 is a... Alright, so let me go and write down this question. Is negative 1 a possible m of L value for an s orbital? And if you think to yourself, okay, what is the range? So for s orbitals, as I said over here, m of L is going to be negative 1 to 0, because remember, it's negative L to L. And you look up here, right here, S is equal to 0 when we're considering the L, right? So if we look back down here, 0 to 0 is equal to 0, right? So it's always going to be equal to 0. So a -1 value for m of L is not possible when considering an s orbital. So that's something you might see on an exam. Shouldn't be too hard. Now let's go ahead and talk about the magnetic spin. All right, so magnetic spin, it has to do with phase, right? So we're basically saying, okay, so are you on the top floor? So we're gonna call this +1/2, or are you on the bottom floor, -1/2? All right, and this apartment complex sort of example is just a way to get you guys to picture it. But the way it actually looks when you look at it in a, most likely you'll get an electron box diagram on your exam. So for example, you might get something like this. Okay, so let's call this our p orbital, right? I don't know if you guys have ever seen these before. Okay, so this is a px, this is a py, and that's a pz. All right. So let's say we had 5 electrons that we had to add to this p subshell. All right. So electron 1 will go right there. Electron 2 will go right there. Electron 3 will go over here. And then, so something important to realize is that when you're filling in electrons into these box diagrams, you always want to draw them unpaired first. All right. It takes more energy for an electron to be paired with someone else rather than to be all by itself. All right. Just like it takes more energy to live with someone in the same room, as opposed to having your own room for yourself, or you know, alone time and stuff like that. That's a simple way of thinking about it. But anyways, once you add that 4th electron, you have to put it facing downwards. All right. Think of this as like a bunk bed. All right. So the first person to get there always wants the top bunk, right? But once people start, extra people start arriving, they have to get kind of like the scraps, and they have to go to the bottom bunk, right? So we filled in our 5 electrons here. These 2 electrons right here, this one and this one, are facing downwards because they got the bottom bunk, right? They both can't share the top bunk because there's not enough space there, all right? And it takes more energy to do that, okay? So magnetic spin is going to be equal to +1/2 or -1/2. And for electrons like this one right here, this one, and this one, the first 3 electrons we filled in, those would be, let me go and write this down. Electrons 1 through 3, the first 3 electrons. Okay, so 5 total electrons. Electrons 1 through 3 are going to be +1/2, all right? And electrons 4 through 5 are going to be known as -1/2 because they're facing downwards. Remember, this is electron 1, 2, 3, 4, 5. All right. So magnetic spin is basically, is this electron facing upwards or downwards? And it's really easy if you know that you should fill up the electrons facing upwards first. All right. So let's say we're looking at a d subshell, and a d subshell is going to be well. Let's go ahead and look at our L values, our m of L values. Okay, so a d subshell. We see right here that d is equal to 2, right, in the angular momentum. So if we were to examine its magnetic quantum number, we would do -2 all the way to +2, right? So -2, -1, 0, +1, and +2. Okay, so if you compare that to over here, this equals 5 rooms, right? Because this is our apartment complex. So we have -2, -1, 0, +1, and +2. And that composes our D subshell. Now let's say we had 7 electrons we wanted to fill in here. Alright, so let's put electron 1 there, electron 2, electron 3, electron 4, electron 5, electron 6, electron 7. Alright, so for electrons 1 through 5, m of s is going to be equal to 1/2. For electrons 6 and 7, it's going to be equal to -1/2, right? Because these 2 electrons, electrons 6 and 7, are facing downwards, right? And electrons 1, 2, 3, 4, and 5 are facing upwards. And that's why we say that they're equal to +1/2 when considering the magnetic spin quantum number. All right. So let me give you guys an example here. So let's say we're considering this following electron box diagram. So an example of a question that your professor might ask you on an exam is which of the following uh, which of the following sets of quantum numbers is possible for the following electron box diagram. All right. So because an electron never stays still, it never stays in a specific point. This is most likely the way that your professor would word a question on an exam, if you did see this on an exam. So okay, so let's go to label this. I'm just gonna call this. I'm gonna tell you guys that n equals 2 here. All right. So based on the amount of windows per se that we have here, so we're gonna call this one -1, 0, and +1, right? So these m of L values, all right. So we just said right here that m of L is equal to -1, 0, and +1, right? So what is this m of what are these values correspond to when considering the L value? So remember that m of L is equal to -L to +L, right? So L has to be equal to +1, right? And when L is equal to +1, so let's go to scroll back up here. We're considering a p orbital, right? Or a p subshell. So for a p subshell, we're going to go and put 1, right? So this right here is the possible range of quantum numbers for an electron within this subshell, right? So now let's examine m of s. Now, since these electrons can pretty much think of these 3 electrons as 3 very hyper kids who just arrived to summer camp or something. All right, and there's 3 rooms, there's 3 kids. They each get to have their own bunk bed, right? So it's not possible for one of the kids to hog a bunk bed and to have 2 bunk beds to himself, right? Each one of them is going to get a top bunk just like they want to, and they're not going to get the bottom bunk because the bottom bunk isn't as cool as the top one, right? So we know that since there's only 3 electrons here, that the only possible value for m of s is +1/2, right? So let's say a 4th kid comes along, and we see this, all right? So that 4th kid can run all over the place, right? He can take any any bottom bunk that he wants within these 3 rooms, all right? So we're gonna say that the +1/2. All right, let's keep that. Okay, so let me get a new color just so I can keep these questions separate. All right. So let's say we add that electron. So when we add that electron, now the possible numbers for m of s change to plus or minus 1/2, right? Because this 4th kid right here, he can jump from this room to the next, to that room, and then back to the room over here, right? He can jump all over the place because he's excited to be with his friends at the summer camp. All right? So that's the way you can think about this. And so yeah, these would be the possible quantum numbers for this given electron box diagram. All right? So if your professor gave you examples such as this one right here, so let's say they gave you n equals 2, L equals 2, m of L equals -1, 0, +1, and m of s equals plus or minus 1/2, you would know that this is wrong, right? Because if L equals 2, then we have to be considering a d orbital. So L equals 2 means d orbital or d subshell. And as we see up here, we're looking at a p subshell, right? So we know that these quantum numbers are not a possible set for this electron box diagram. All right. So hopefully you guys understand electron box diagram so far. Let's go and get into electron configuration. All right. So I actually got this picture. It's probably gonna pay super duper big. Oh, never mind. So so this is an easy way of doing electron configuration. All right. So let's go and start off by trying to get the electron configuration for oxygen. Let me zoom out a little bit. Okay, so we're going for oxygen, all right? So oxygen, how many electrons does oxygen have? So let's look at the periodic table. Oxygen in its neutral state would have 8 electrons, as seen right there. So 8 electrons, right? So let's go ahead and write the electron configuration for those 8 electrons. Okay, so the first step you should do is just imagine that this helium right here is going to slide over here. So it's going to draw in helium over here. So He, and this is atomic number 2, right? So we already considered helium over here next to hydrogen, all right? So we're gonna call this. So the first 2 groups are here. We're gonna call them the S block, all right? S block. We're gonna call the middle metals the D block. And then the non-metals over here, mixed with them with metalloids and some metals, we're going to call this the P block. And these down here, these are known as the F block, but I highly doubt that you'll have to know any sort of electron configuration for the F block in General Chemistry 1. I saw it when I took General Chemistry 2, so you might want to learn it now, but I won't be going over it in this video. All right, so in order to start writing the electron configuration for oxygen, we have to start over here, all right? So we know that this is row number 1, right? So let's go ahead and number our rows. This is row number 1. This is row 2. Yep. And that's row number 2. That's row number 3, 4, 5, 6, and 7, right? Just like it has over here on that 1S, all right? So the first thing you do is you have to look at your row, all right? So we're in row 1, right? So let's go and write a 1. And we're in the S block, so it's going to write an S, 1S. And in order to fill up those 2 electrons, remember, we're completely filling up those 2 electrons because we're trying to get to a total of 8, right? So 1S2, all right? And we look over here, we go across over here, and we see that there's nothing left over there because remember, we crossed off that helium, all right? So it's going to start back down on this second row, all right? So let's go and write the 2. And then we have 2s2 again, right? So 2s2, and after we do that, we go across over here, and we see that there's a 2p on the other side, right? So it's going to write 2 again and p. But notice that we've already written down 4 electrons, right? Because we have 1s2 and 2s2 adding up to 4 electrons, and we're trying to get to a total of 8 electrons because oxygen has 8 electrons in its neutral state. All right, so in order to write the electron configuration for oxygen, we need to still add 4 more electrons, which is we can get from right here, 2p4, right? And if you count, all right, so this is 2p1, this is 2p2, this is 2p3, and 2p4, right? And if we were going for fluorine, we would write 2p5, and neon would be 2p6. Do you guys see a trend here? I hope you do. All right, so yeah, this is the complete electron configuration for a neutral oxygen atom. All right, so let's go in and do something a little bit further down the periodic table. Let's go for chlorine. All right, so for chlorine has 17 electrons. Right. So let's go and start over here again. So we have 1s1 under hydrogen. We have 1s2 under helium, so it's going to write that. So 1s2, and then we look across the periodic table. There's nothing there, so we skip a row. All right, so 2s, 2s1 with lithium, 2s2 with beryllium, so 2s2. We go across the periodic table, so 2p6, right? 2p1 with boron, 2p2 with carbon, 2p3 with nitrogen, 2p4 with oxygen, 2p5 with fluorine, 2p6 with neon. Alright, so we still haven't added up to that 17 total of electrons that we want. Alright, so let's go further down the periodic table. So we go down to the 3s, right? You have to go back to 3s. 3s2, alright, so 3s1 from sodium, 3s2 from magnesium, alright? And so far we've added up to 2, 4, 10, 12 electrons. We still need 5 more. So let's go and count down here. So 3p1, 3p2, 3p3, 3p4, and 3p5. Do you guys see how this 3p5 adds up to chlorine? So we already said that this was a total of 10, right? Actually 12, sorry. And with this 5 right here, we now add up to 17 electrons, making this the complete electron configuration for chlorine. Alright. Now, let's say we're considering the chlorine anion. Alright. So when chlorine gains an electron, for example, in when it forms hydrochloric acid, for example. Alright. So hydrochloric acid. That hydrogen is going to share its electron with chlorine, so that they both look like a neon, like a noble gas, right? So if hydrogen gains an electron, it looks like helium. And remember how at the beginning of the semester, I told you guys that all atoms basically want to. The whole name of the game of chemistry is to look like a noble gas, because if you look like a noble gas, then it means you're more stable than if you look like whatever you were before. All right. So hydrogen gains an electron to look like helium, right? And chlorine is going to gain an electron to look like argon, right? So when we consider let me write H plus and let's do the sodium plus and Cl minus, right? So Cl minus, we're going to do the electron configuration for Cl minus. So let me get a different color and let me rewrite that just so it doesn't confuse you guys. So we're doing Cl minus, right? So we start off with 1s2, right? Then we go down the periodic table to 2s2. Then we go across to 2p6. Then we go down a row to 3s2. Then we go across the periodic table and we do 3p. Let's see. So chlorine minus has 18 electrons, right? And so far we have 2, 4, 10, 12. And in order to get 18, we need 6 more, right? So 3p6. Notice that now that chlorine has 18 electrons, it looks exactly like argon. All right, so I'm gonna go ahead and erase this F block because we don't really need it. And let's go and do the electron configuration for argon. So 1s2, go across the periodic table. There's nothing there, so go downwards, and you get 2s2. All right, so 2s2 over here, then 2p6. Then you go down the periodic table to 3s2, then 3p6, right? Because argon has 18 electrons, and right here we have a total of 18 electrons as well. All right, so that's the electron configuration for argon. And notice that they're the exact same thing. So when two things are exact same thing, although they're not the same element, right? So chlorine minus is not the same thing as argon because they have differences in protons, right? Chlorine has 17 protons while argon has 18, making them two separate and unique elements, right? So when chlorine minus and argon have the same exact electrons, we see that they are isoelectronic. Sorry, so isoelectronic. When an element shares the same electron configuration as a or with a neighboring ion. Alright, so this isoelectronic also will work for a positively charged cation, right? So we saw how it works with Cl minus. It would also work with S2 minus as well as P3 minus, alright? And they would all have the same exact electron configuration as argon and chlorine we see here, but it can also work for potassium, right? So potassium normally has 19 electrons, as we see over here. So neutral potassium has 19 electrons. But when you make potassium plus, because potassium, in order to look like a noble gas, it has to give away an electron, right? It's easier to give away an electron than gain 7 to look like krypton, right? So we're going to give away an electron, and we're going to get a total of 18 electrons, right? Just like argon and just like chlorine. So in this case, we would say that Cl minus, argon, and potassium plus are all isoelectronic. And they are isoelectronic because they share the exact same electron configuration. Alright? So before we move on to paramagnetic and diamagnetic, I want to show you guys an example of how to do one of the 4p electron configurations. Because they're a little bit different just because we see that we cross the D block here. Alright? So let me get a different color. And let me I'll just get a thicker color, and I'll zoom out a little bit just so you guys can see everything. Alright? So let's do the electron configuration of bromine. Alright? So bromine has how many electrons total? Well, let's see. A neutral bromine has 35 protons, right? So in order for it to be neutral, it has to have 35 electrons. Alright? So let's go and start off the electron configuration. Alright, so we go to the first row over here, and we see that we have 1s2, right? Then we skip a row, go 2s2, we go across the periodic table over here, and we hit 2p6. Sorry, 2p6. Then we have 3s2, then 3p6, then 4s2, then 3d10. Notice how we went to 3d10 instead of 4d10, and this is kind of weird, but just remember that we always skip the first row. We always skip the first row when we're considering the D subshell, right? So right here we went straight to 3d10 instead of 4d10, right? So I hope you guys can see that, and make sure you do that on your exam if they ask you for something like this. So next we have to go into the 4p, right? But let's see how many electrons we need. So we could do it two ways. We could count 4p1, 4p2, 4p3, 4p4, 4p5. I don't know if you guys can see that, but we ended up with 4p5, right? Or we could have done it the mathematical way. Alright, so we know we need 35 total electrons, and there's 2, 4, 10, 12, 18, 20, 30. Right? So 35 minus 30 makes 5, right? So there's two ways you could do that. If you don't like the way I'm showing you, you could do the mathematical way. Alright? So yeah, that would be the electron configuration of bromine. Okay? So there's one last thing I want to show you, and it's fairly easy. Okay, so let's do an example. Okay, so let's go back to this oxygen example. Alright? So we know that the electron configuration of oxygen, neutral oxygen, is 1s2, 2s2, and then 2p4, right? So let's go ahead and draw this electron box diagram. Alright? So something that you guys should realize is that these are all of the valence electrons, right? So the 2s2 and the 2p4 would be the valence electrons of oxygen. So all the electrons inside the outermost energy level would be the valence electrons. Alright? So the 2s2 and then 2p2 would make up the valence electrons for oxygen. And yeah. Alright, so let's go ahead and draw the valence electrons here. So we have a 2s2. So there's 2 electrons in our s orbital, so it's going to fill those out. And we have 4 in the p. Alright, so this is s, and we'll call that box 0. This is 0, -1, +1. And this is a p subshell. Alright, so px, py, and pz orbitals. Let's go ahead and fill out our 4 electrons. Okay, so we have 1, 2, 3, 4 electrons there. Right. So let's go ahead and draw that one out, and let's also go ahead and draw argon. Right. Remember we said argon was. Let's go ahead and draw out the valence electrons. So argon. Let me do this in red again. Argon has 18 electrons, and it has 1s2, 2s2, 2p6, 3s2, and 3p6, right? So let's go ahead and draw out the valence electrons, which is 3s2 and 3p6, right? So we have the 3s, or the 3s orbital, right? And this is box 0, so 1, 2. And then let's go and draw out the px, py, and pz. And this is box -1, 0, and +1. And we have 6 electrons, so 1, 2, 3, 4, 5, 6. So all of them are paired up, right? So paramagnetic and diamagnetic, it's basically it's labeling elements that give off a magnetic field. All right. So when you have unpaired electrons, for some reason, I don't really know why, but they will emit a magnetic field. All right. But if you have all paired up electrons, they won't emit the same magnetic field. Okay. So when we look at oxygen, do we have any unpaired electrons here? Well, let's see. All right. So we have these 2 are paired, right? But these 2 are not. So this electron and that electron are not paired, correct? So we label this as we label this as paramagnetic, because we see that there are unpaired electrons. It doesn't matter if you have it doesn't matter how many electrons you have that are paired. If only one of them is unpaired, you label that that element as, or that element or ion as, paramagnetic. All right. But if you see something like this, all right, we see that these are paired, those are paired, those are paired, those are paired. So this is going to be called diamagnetic. Not very good at spelling. Diamagnetic. All right. So let me go ahead and summarize that down here. So paramagnetic is when you have unpaired electrons. And diamagnetic is when all electrons, and we underline all, are paired. Alright? So it's very, very important that you guys realize that all the electrons have to be paired, alright, in order for it to be diamagnetic. If only one of them is unpaired, it's considered to be paramagnetic, right? So I think that's pretty much it for this module. If you guys have any other questions or need any clarification on anything, don't be afraid to email me. I hope you guys enjoyed this video, and I hope it was useful to you guys. And remember to do your assignment for next week. Alright, so thanks for watching.